let's talk about the reactions that I've been skipping, like that are at the tail end of each lecture day that we never get to. They're less important from a mechanism standpoint, but they're important to know. And obviously, they're covered. There are lecture videos that show the mechanism on this in the pre-recorded, but I thought it would be nice to just put them on the board one slide so you see them. One of those is the Wolff-Kishner reduction. Which converts a carbonyl group to a CH2, completely removes the oxygen. So it's a reduction in the removal of oxygen sense and a reduction in the added hydrogen sense. The second is cyanohydrin formation. And that takes a carbon oxygen double bond and adds HCN across the double bond. Third is the Baeyer-Villiger oxidation. And what that does is convert ketones to esters. So useful functional groups, this cyanohydrin group can then be converted to lots of other things. And once you have an ester, right, you can hydrolyze and clean up that ester. So they're pretty simple in terms of just writing the reaction out. The Wolff-Kishner reduction is very much related to imine formation, mechanistically, except that it's base catalyzed instead of acid catalyzed. So you can take cyclohexanone, treat it with hydrazine and base, and AOH. And the other products are nitrogen gas and water, and that's why the reaction is so favorable, because the nitrogen gas goes out of solution, so that's not reversible. The mechanism is a bitch. This is a 10-step mechanism. But I think 7 of them are proton transfers. It's all taking protons from one place and putting protons off the other place. And I showed it in great detail in one of the other videos if you want to watch the mechanism. But effectively, it's a base catalyzed imine formation. And you know base catalyzed reactions generally involve fewer steps in acid catalyzed reaction. So the imine forms in only 5 steps instead of 6. And then after you form the imine, that imine breaks down because you've got acidic hydrogens on the nitrogen. So it's 5 steps to get there, and then another 5 to take that imine and break it down further. And basically what you're doing is you're taking a proton off the nitrogen, putting a proton on the carbon, taking a proton off the nitrogen, and then nitrogen gas. So I'm not going to show that mechanism because we just don't have time to go through those 10 steps. But what you need to know is if you have a carbon oxygen double bond and you need a CH2, one way to do that is by adding hydrazine and hydroxide. It's got to be hydrazine, can't be just any old amine. Hydrazine and hydroxide. It's a good method as long as your molecule doesn't have anything base sensitive elsewhere in the molecule. The other way that you've seen, that I didn't cover explicitly, of converting a carbonyl group to a CH2 is to to go through the thioacetal, and then treat that with hydrogen gas or anything more. That also chops that off. It's called radial desulphurization. So it's another way of converting a carbonyl group to the CH2 by first adding the 1,3-propane dithiol with the Lewis acid catalyst like zinc chloride to make the dithiazine, and then radial. So it's a useful reaction synthetically. It's an important reaction to have in your toolbox. Cyanohydrin, by contrast, the mechanism for cyanohydrin formation is the simplest mechanism you'll see. This one's the most steps, this is 10 steps, but cyanohydrin formation is 2 steps. It's usually done by taking your aldehyde or ketone, whatever your aldehyde or ketone is. There's aldehyde, and you have NaCN, and you add some HCl, but not a full equivalent. Since HCN is a pretty weak acid, cyanide is a decent base. So it gets appropriated pretty readily. What you want is you want to add enough HCl so you form some HCN. And as long as you have both the cyanide ion and HCN in solution at the same time, you can get the nucleophilic addition of the cyanide ion. And because it's a decent base, the first step is going to be nucleophilic attack, which is actually also here. Right? The first step is nucleophilic attack with nitrogen lone pair. So you're going to add cyanide. And then HCN is going to propagate back again into cyanohydrin. It's an equilibrium reaction. So very simple, right? Nucleophilic attack in step 1 by cyanide. And then protonation of step 2. That is the simplest base catalyzed or base controlled reaction of a nucleophilic acyl addition. Base adds, protonation. So all you have to do is you have to control the pH so that you've got cyanide ion present and HCl present at the same time. And this reaction will go. The reaction would also go if you ran it in liquid HCl. But liquid HCl is toxic and nasty, and you don't really want to deal with that. So it's typically added as a cyanide salt, and then you just generate the HCl in situ as you need it. The reason why they matter is, though this is base sensitive, right? The reaction is readily reversible at base. Under acidic conditions, you can convert that cyanide to carboxylic acid, and from then to every carboxylic acid derivative that's available. So you can make lots of other things from cyanide. It is a carbon-carbon bond forming reaction, right? Because you made this new carbon-carbon bond here. Cyanide ion can also be reduced in lithium aluminum hydride generate amines. Because lithium aluminum hydride is basic, but you have to protect first. But as long as you protect that alcohol so that the basic reagent doesn't deprotonated and reverse the cyanohydrin formation, you can make amines out of cyanide ion. So it's a good precursor to lots of other things that you might want. So very simple mechanism. Right? The Wolff-Kishner is the largest number of steps, I think, of any of the mechanisms we'll do, and cyanohydrin is the smallest number. The Baeyer-Villiger oxidation is in between the four-step mechanism and it's the second example you've seen in the course. Of a reaction with a peroxy acid. So it can be done with MCPBA, although that's not the only peroxide that will do it. Take 2-methylcyclohexanone and treat it with this peroxy acid. And it doesn't have to be that metachloro, it could be acetic, like just something that's attached. This is significantly more acidic than a regular acid. Because you've got the extra oxygen in there, which means the equilibrium reaction for it protonating the carbonyls can be favorable. Writing this as R, so I don't have to keep writing that ring. Right? So it's different from the two reactions we just talked about, Wolff-Kishner and cyanohydrin. Those, the first step is nucleophilic attack. This one, the first step is protonation because we're in acidic solution. And then there's nucleophilic attack. When you've done a nucleophilic acyl addition reaction in 2 steps, but this time under acid conditions. Where you simply added the peroxy acid across the carbon oxygen double bond with the nucleophilic oxygen going to the carbonyl carbon and the acidic proton going to the oxygen, right? Nucleophilic acyl addition can happen either by protonation followed by nucleophilic addition or nucleophilic addition followed by protonation. Because this bond is really weak, though, and wants to break, the next step is association. There's an alkyl shift. That is not a reversible step. So carbon 1 will have that positive charge on it because the alkyl will just move, and the other product will be resonance stabilized carboxyl media group. And that will deprotonate this hydrogen. To generate the final product. Lactone, in this case, a cyclic ester is called a lactone. The more substituted group has a larger migratory aptitude. So a tertiary would move first, and then a secondary, and then a primary is unlikely to move. And the reason for that is you've got positive character, right? Both of these kind of are partially positive. This is got partially negative here. Because you've got positive charge in the transition state, the carbon that's more able to stabilize the partial positive charge is the one that's going to be. That's it. We're over time a little bit again. Not too bad. So those three reactions were the tail end of each of the three previous lectures that, kind of hung out there, didn't get gotten to. There's a problem set on the Baeyer-Villiger oxidation where you can practice like making sure you move the right group and get the right ring size and all that shit. So it would be a reaction quiz Tuesday. No mechanisms. So you should know the alkyl condensation. You have to draw the product, but not worry about the mechanism yet. You should know these reactions. Obviously, you should still know the Villiger reaction. I think it's problem 44. And the end of chapter 17 has got a whole bunch of reactions, like treat this tube with all the same things.
I was trying to do that last night with Max, and
yeah, so that'd be a
we
good
were
problem.
so confused. I'm like, well, how does this nitrogen thing
so
just like poof into
poof magic.
nothing?
So that would be a good problem set to kind of focus on and helping you prepare for the quiz. And just make your note cards, write all your reactions out. We've now done all the reactions from chapter 17. We haven't finished all the ones from chapter 18.
Cool.
And then the mechanism quiz next Thursday will be the alkyl condensation mechanism, so you've got extra time to master that.
Wonderful.
Yes, it's wonderful. Oh, Chem is wonderful.